Welcome to Fermilab's Dark Matter Day. We have a number of people here from Fermilab that are going to tell you about our search for dark matter. We have scientists and grad students all excited to share their science with you. I'm going to go through and tell you a little bit about who's going to be talking today. So first off, we have Dan Bauer. Dan is a senior scientist at Fermilab who has been searching for dark matter with his laboratory experiments for 20 years. Then we have Krnjaic. Gordon is a Fermilab theorist who's working to understand the particle nature of dark matter. We've got Lauren too, Lauren is a Fermilab scientist working on the SuperCDMS experiment. We've got Noah Kurinsky. Noah is a scientist at Fermilab developing new detectors to search for light dark matter. We've got Ankur Agrawal. Ankur is a graduate student at the University of Chicago working at Fermilab on the ADMNX experiment. We've got Alex Drlica-Wagner. Alex is a scientist at Fermilab working on DES and LSST telescopic surveys for evidence of dark matter. And I promise they're going to explain all of these acronyms for you. Nhan Tran. Nhan is a scientist at Fermilab working on LDMX and CMS accelerator searches for dark matter. Matteo Cremonesi. Matteo is a scientist at Fermilab working on the CMS collider search for dark matter. And they are all going to share a little bit about their work with dark matter. And with that, I'm going to pass it over to Dan, who is going to kick us off today.
Thank you, Becky. Thanks to all of you who are joining us today. Let me start this off by showing you a few slides on what is dark matter and why does it matter. Okay, so when we look into the universe, we see some form of material that doesn't emit or reflect light, and you could picture that by having this light bulb and this material in your eye, and the light just goes straight through this. Doesn't scatter, just zips through. Whereas the matter we're used to, normal matter, would absorb or scatter that light, or possibly you can just be staring at the light bulb and you're seeing the light directly. So there's some form of matter in the universe that might have been better called invisible matter, but it doesn't seem to interact with light or any form of electromagnetic radiation. So why do we believe it exists if it doesn't interact with electromagnetic interaction that we know about? Well, there's a lot of evidence for it. And one of the earliest pieces of evidence that dark matter exists came when people used telescopes to look at how galaxies and galaxy clusters rotate. So if you look at the speeds of stars on the outskirts of galaxies, instead of falling off as you would expect for the mass of the stars and the gas in the galaxy, they don't. They stay constant all the way out to the edge. The only way that can happen is if there's a lot more matter in the galaxy than you can see in the stars. So that was one of the first pieces of evidence. It wasn't widely believed at the time, but there are other pieces that have come up. So another way of looking at the universe is to look out even farther and see clusters of galaxies. And there are galaxies that can be behind those, and you see that light is bent. This is something that Einstein predicted a long time ago, that light would be bent by the mass in the galaxies. But it's bent far more than the mass of the galaxy cluster that we could infer from just seeing the light. You see this by seeing these things like blue arcs around massive clusters of galaxies. And in order to form some of the arcs that we see, then you would have to have matter like this shaded in blue, which is far more matter than what we see. That's another piece of evidence for dark matter. One of the more striking ones that was noticed is what happens when galaxy clusters collide. So in this simulation, blue represents dark matter and pink represents normal matter. You see the two clusters collide. And what you see is that the blue dark matter just sails right through without interacting, whereas the pink normal matter slows down. It interacts with other normal matter. And in fact, this end picture is a real picture of galaxy cluster collision that we've seen in the universe. So that simulation is borne out by what we actually see. And then another really strong piece of evidence is the fact that we're here at all, that there's galaxies and clusters of galaxies. If there were only normal matter in the universe, they wouldn't have formed at the time that we live since the Big Bang. This is a simulation of just dark matter that was produced in the Big Bang. And as you see the time elapses, you see that dark matter is actually coming together. Don't be fooled by the glow. It's not actually glowing. That's just the way the simulation shows us that dark matter is coming together and forming what you could call a cosmic web. And that cosmic web actually was the seed for pulling in normal matter and forming galaxies and clusters of galaxies, the things that we see in the universe today. And this is actually a result of a survey, a telescopic survey that shows you that web, this time revealed in normal matter. This is stars and galaxies, but it's outlining how the dark matter pulled things together. So if this picture is all correct, the Milky Way galaxy that we see, looks something like this. That's not actually all there is to it. There's a huge halo of dark matter that surrounds and is within that galaxy, our galaxy. So that implies that dark matter is all around us. So I've told you some of the evidence of why we believe there is dark matter. Let me throw it over to Gordon now to tell you some possibilities for what dark matter might be.
Thank you, Dan. So what could dark matter be? Let's first start off by talking a little bit about what we know about visible matter. So the stuff that we're all made of, we've learned over the past 100 years is made of atoms. And if you zoom in on the atoms themselves, we know that we're made of protons and neutrons and electrons and a host of other more exotic particles on even smaller scales. And what we've learned about those smaller particles is that they're held together by four fundamental forces. Dan already mentioned gravity, which is the universal attractor between all forms of matter. But we've also discovered electromagnetism, the force that allows like charges to repel and opposite charges to attract, and it holds together the atoms. But we've discovered the strong force as well, and this is what holds the nuclei at the middle of atoms together, and it's much, much stronger as its name suggests. This only applies to quarks and gluons, the constituents of the protons and the neutrons. And finally, the weak force, which is responsible for radioactivity and for the decays of unstable particles. As most of the particles that we have discovered don't live for very long, they quickly decay and become other kinds of particles which are stable, like the kinds that we're made out of. So what does that mean for dark matter? What do we know about dark matter? Well, as Dan told you just a moment ago, all the evidence that we have for it so far is based indirectly on how dark matter pulls on other things gravitationally on very large scales. And if we're unlucky, that could actually be the whole story, that anything beyond just dark matter interacting gravitationally is on some level optional. But fortunately, many of the other possibilities involve features that help us craft detection strategies. One thing we do know for sure is that dark matter has to be stable or very long-lived, because we know that it's been around for the entire cosmic history of 14 billion years. And that's required to account for the evidence that Dan told you about, because some of the light that's left over from the Big Bang itself carries the fingerprints of dark matter having been around all the way back then. And it's still around today from what we observe in galaxies. So it has to be quite stable. Dark matter has to move very slowly compared to the speed of light. That's not actually a huge restriction, but if dark matter were moving very fast, if it were as fast as a photon or a neutrino, particles that move very close to the speed of light, it couldn't clump successfully to form the seeds of galaxies, which is one of the things that dark matter has to do. And importantly, you might wonder, could it just be normal matter in disguise? And the answer is that it can't be, because otherwise we would observe far too much helium and lithium and other small elements than we observe in the universe today. And the logic for this is that even though most of the elements that we observe were formed in stars at much later times, it turns out that the lighter ones were formed very early, and the amount that was formed is dictated by the amount of total matter that was around back then. And so if dark matter were just another form of normal matter, that would lead to the production of more helium and lithium, which we don't observe. And finally, we know that dark matter can't interact very much using the strong or the electric force, because otherwise we would see the light that would come as a consequence of having these other ways of interacting with us, or it would have been produced in accelerators already. So finally, dark matter might interact using the other forces, namely the weak force, which is responsible for radioactivity. That's still a possibility, or a new force entirely that we haven't yet discovered, but might discover by studying dark matter more. So there's a huge range of possible dark matter masses. So here, don't worry too much about the numbers, except to just get a visual impression of how much variability there is, given what we have in the evidence data so far. So comparing the mass of a proton, which we can just call 1 here, we have a list of other particles that we've discovered thus far, as some subset of those. And dark matter, as far as we know, just based on the evidence that we've collected, could be as light as 10 to the minus 31 times, an astonishingly smaller number than the mass of a proton, or almost as large as the Earth itself as we get to the very high end. On the lower limit, dark matter has to be of just the right size to be able to fit inside the smallest known galaxies. And on the upper limit, ultra heavy dark matter would already have been observed through its effect on the bending of light on very small scales. So on the smallest end of possible dark matter, we have wave-like so-called axion dark matter. And this is a dark matter candidate that consists of very light, very slow particles with very feeble interactions. But it has this property that it is actually unstable. And if you wait long enough, an axion-like particle can turn into 2 photons, which we can observe. And there are experiments to look for these. Similarly, dark matter could be what we call a sterile neutrino. This is a heavier neutrino than the ones we've already discovered. So in nature, thus far, we've discovered 3 particles which are neutrinos, which are very light particles that don't feel any electric charge, and they move very close to the speed of light. But we know that's not allowed for dark matter. So if dark matter were a slightly heavier version of that, that would be a reasonable possibility. And if that were the case, then you would be able to see the sterile neutrino, if you wait long enough, turn into a photon and one of the known neutrinos. And this is another way to discover it. Dark matter could also interact with us with a known weak force. It could be a weakly interacting massive particle. If it's a little bit heavier, around maybe masses between the mass of the electron and the Higgs boson. So something between lighter than the proton or heavier than the proton, but in that same ballpark. And there the dark matter can hit atoms as it passes through the Earth. And then we can observe the effect on those atoms inside of a detector, which we'll hear about later, based on how it influences the matter that's inside of the detectors themselves. So this is a promising strategy for searching for dark matter. And even cooler, maybe, is that dark matter can be a black hole. Now, black holes, when we think about them, are these objects in our universe that don't emit any light. And if you get really, really close to them, you can't escape anymore. And so they don't emit anything. If they formed 14 billion years ago, not from the collapse of stars, as we might imagine black holes forming today, when stars reach the end of their life cycle under certain conditions, these would be black holes that formed in the very, very early universe through processes that are unlike the collapse of stars. And this remains one sensible possibility in a particular mass range. So with that in mind, I'll just remind you that this is only a small slice of many other possibilities. This is a very active field of study, and we should remember that it could also be more than one thing. We're made of many things, and the dark matter could also be. So this is still a very exciting topic. Thank you. Back to Dan.
Thanks, Gordon. So both Gordon and I have told you that dark matter may be all around us. It may be part of our galaxy. It may be passing by us right now. It may be interacting with materials in the lab, albeit not very often. So behind me is, in fact, some of the typical apparatus you might use for dark matter. This is a very special kind of refrigerator to cool down detectors that you'll hear about a little bit later that look something like this. This is a semiconductor made of silicon that we've used in the past to search for dark matter. Let me show you something that might help you understand a little bit more about how dark matter might interact. So this model is a model of an atom, a crystal, where the tennis balls are nuclei and there are springs between them which represent the electrons that form that hold the crystal together. So if I have a dark matter particle, which I'll show you a nice one, most of the time it will just go right through and nothing happens. The crystal doesn't even see it because dark matter almost never interacts with normal matter. But if Gordon's right and there's this fifth force or some new kind of force that affects dark matter, then our friendly special dark matter particle may occasionally come in and hit that nucleus or sometimes an electron and cause the crystal to vibrate a little bit. That is energy released in a detector. That vibration can be sensed and brought out into a signal that we can record. However, if the crystal is at room temperature, it's doing this all the time. That's what we know as heat. It's vibration of atoms. And you can see that if the crystal is doing that and I drop my dark matter particle in, nobody's going to know, because the crystal is just jiggling way too much. But if I use that refrigerator behind me and cool down this crystal, that damps out all of the motion of the crystal. And now if I drop my dark matter in, you can see there's still a little vibration because it's not totally frozen, but you can still see the interaction above and beyond that vibration. So that's one of the ways that we're trying to search for dark matter in the laboratory. And let me turn it over now to Lauren, who's going to tell you much more about a specific type of experiment that's searching for that sort of heavier dark matter. Okay, take it away, Lauren.
Okay, thanks, Dan. Let me just go to the slideshow so you can see better. Okay, so yeah, so as Dan was demonstrating, as an experimentalist, you need to know what your signal might look like if you build an experiment. So one thing that you want to understand is how dark matter is distributed. in the universe. And so from the gravitational interaction that we see out there, we have some idea of how dark matter is distributed. And from all the studies we've done, we believe that dark matter is moving at a speed of something like 600,000 miles per hour relative to Earth. And so, actually, sorry, I should take a step back here. So as you heard from some of the previous slides, dark matter is all around us. And in fact, it's actually distributed in what we call a big halo around our Milky Way galaxy, which is essentially a cloud. And so because the sun is moving around the center of the galaxy and the Earth is moving around the sun, there's actually what we would call a dark matter wind relative to us. And so how fast is that wind? Well, it's about a 600,000 mile per hour wind. And that seems fast to us on Earth, but as you heard from Gordon, we actually say that that's slow for a subatomic particle because it's much, much less than the speed of light. So I work on an experiment that looks for what we call heavy dark matter, though heavy is a relative term. And so in this case, it means a particle that's about the size of a nucleus, something like a xenon, something like the element xenon, for example. And so if you take the assumption that dark matter weighs as much as a xenon nucleus, then we can predict that there's about 10 million dark matter particles passing through an area about the size of your hand every second. And so as Dan showed you before, dark matter interacts very, very infrequently. And so most of the time that dark matter just goes right through. And so you might be alarmed to think there's 10 million dark matter particles passing through your hand every second, but they're really just not doing anything. In fact, the interaction rates are so low that we predict if we were to build a large dark matter detector, we would only expect to see on the order of 1 dark matter scatter a year in a detector that's a multi-ton size detector. So one of the problems that you have to solve as a dark matter experimentalist is how to distinguish dark matter interaction from something that is much more ordinary, such as ordinary particles from radioactivity, made of common matter that we find here on Earth. And so what we find is that there's trace radioactivity in most materials, a very, very small amount, but it turns out because dark matter interacts so infrequently that the expected dark matter scattering rate is 10 million times lower than the particle interactions from radioactivity, from the trace radioactivity in your materials. So in a lot of ways, it's like looking for a needle in a haystack. I think it's probably, I don't know how many strands of hay are in a haystack, but I think it's actually probably more like looking for a needle in several haystacks and not even being sure whether the needle is there. So this is the problem of the experimentalist, which is how to separate your dark matter interaction from what we call background, which is interactions from normal matter particles such as photons, electrons, and neutrons, which also scatter off the nuclei and the electrons, just like dark matter. So what you do as an experimentalist is the first thing you have to do is carefully select the materials for your experiment. So the materials that you use, you want them to have very low levels of contamination from things that have radioactive decay. But it turns out practically that's difficult because basically dirt has trace amounts of radioactivity in it. So you have to build things that are very, very clean and very, very pure. So as an example, consider that the residue from your fingerprint can leave 20 times more background than an expected dark matter interaction. So for example, if you build your beautiful dark matter detector and you touch it with your finger, there's potassium 40 in our bodies, and that produces gammas and also betas, and you will actually see those interactions. So we're looking for contamination at the level of 1 part per billion, or sometimes less than that. And so you actually need to build special detectors just to screen the materials that you build your dark matter detector from, to check that there aren't these radio contaminants in them. So after you do that, you still actually need to surround your detector with what we call shielding. That's because these detectors are so sensitive to particle interactions that even if you build your detector out of radio pure materials, you will still see the trace radioactivity from things that are near your detector. For example, the wall or the floor, the wall of your lab or the floor of your lab or your dilution refrigerator. So you have to actually find radio pure shielding, and we like to use lead and polyethylene as an example. And you have to surround your detector with that to basically shield it from the environmental radiation. So finally, particles from space can also produce a background for your dark matter search. These are very difficult to shield against. You could try to surround your detector with more shielding, but in practice, you actually need kilometers of Earth to shield from these particles. And so what we do is we actually build our experiments deep underground, usually in mines, because there's already infrastructure. Sometimes they're abandoned mines, sometimes they're active mines. And I'm gonna just tell you briefly about an experiment I'm working on called SuperCDMS, which is being built at the SNOLAB underground laboratory, which is in an active nickel mine. And that particular lab happens to be about 2 kilometers underground. And so this is just a schematic of SuperCDMS. In this case, the experiment itself consists of 50 kilograms of crystal, semiconductor crystal. And as Dan described, we also have background from heat. And so in order to see those dark matter scatters, we have to cool our detectors down to 40,000th of a degree. So not 40,000, but 40 thousandths, which is 1/1000th of a degree above absolute zero. So this is extremely cold, and we use a special refrigerator called a dilution refrigerator to do that. So SNOLAB is being built at, SuperCDMS is being built at SNOLAB, but major components of it are being built at Fermilab. And so I don't have time to show you a video, but if you're able to follow this link, this is a fun video which shows a day, what it's like to work at SNOLAB for a day. And so, you know, you have to get dressed in special gear for going underground, and you go, you ride what we call a cage down there with actual miners because it's an active mine. And then because it's an ultra clean lab, because we have to avoid tracking dirt with radio impurities into the lab, you have to take a shower before you go in there. So it's pretty involved, but it's a fun video to watch. And this just, this is a complicated diagram, but it was just meant to show you roughly the scale of the experiment and the complexity. And so there's a little silhouette of a person there to give you an idea of the size. And in the upper right there, you see our detectors, which are 10 centimeters by 3.8 centimeters, and we have a couple dozen of them. And so these are very small detectors, but we need all this, many tons of radio pure shielding to prevent the environmental radiation from producing a background in our experiment. Okay, so back to you, Dan.
Thanks very much, Lauren. Now we're going to turn to Noah, who's going to describe an experiment we're actually doing on the Fermilab site, searching for light dark matter. Take it away, Noah.
Thanks, Dan. So this will be one of the few times where you actually do see a video. So I'm going to set this up a little bit. Lauren explained pretty nicely why, you know, we have to go to SNOLAB for some of these heavier dark matter experiments. When you do probe lighter dark matter, so about 1,000 times lighter than a proton, there's a lot more of it around. Like we know there's what the density in terms of mass is, and so if the particles are lighter, there's just more of them in a given volume, and so we don't have to go as far underground, and we don't need to use as much mass to probe things. So there's actually 2 experiments that are and have been running at Fermilab, only about 100 meters underground. So those of you who've been to the site will recognize this is the Wilson Hall, it's the main building. There was a neutrino experiment called Minos that built this cavern underground, and we're using one of the side drifts here, both experiments, to run, you know, a few grams of new detectors and search for dark matter in Batavia. and I guess I can actually go full screen. So the Sensei experiment, they basically use really nice scientific cameras to look for dark matter. So they can, this is a slide that sent to me last year for this dark matter day. And so they've been running at Minos in the top left picture, as well as now that they've prototyped their detectors and they think they understand them really well, they are actually moving to SnowLab, which is the facility that Lauren was just talking about. But running these things even for a few hours, usually if the detector is improved over previous generations, allows you to set sort of brand new limits on dark matter. So this is really driven by R&D into improving detectors and letting them see smaller energy deposits. The thing I'm involved in is this Nexus facility. So it's a dilution refrigerator that sits down in Minos, and we are running a very scaled down version of the detector that Dan showed you. This is only about 1 gram in size. But what we do here is we try to get, we try to see smaller and smaller energy deposits. And as we do that, probe new backgrounds and set some new limits on lighter dark matter candidates. So what I'm about to show you is a version of me that's a year younger and doesn't know the word coronavirus. So we did do a live stream for Underground last year, and here's a little bit of a clip showing you Nexus, where I explain a little bit about how the detectors work and show you around the facility. So a clean room, it just has this flow of air as a vertical sheet that takes all the particulates out of the air and pumps them out the vents in the side of the room. If you look over here, this is our fridge. So it's a fridge just like you have in your kitchen, except instead of getting down to like where water freezes, we get down to fractions of a degree above absolute zero. So right in this region, here, we have our little experiment. I'll show you that detector that we have in here in a second. Not the same one, but an exact copy. Right here is 13 thousandths of a degree above absolute zero. It's surrounded by a couple shields that are at different descending temperatures. And again, I'll show you actually what the status of those are. An outer vacuum vessel, and then this blanket here that you can see, which is a special material designed to repel magnetic fields. So at the center of this volume, if you could see it, you'd see a tiny little detector surrounded by all of these layers of copper and aluminum and magnetic material and even lead that shield it from light and from radiation and from magnetic fields. So it's a very sensitive, ultra quiet environment in here. We're in this big clean room underground where we're shielded from cosmic rays and from lots of extra electrical signals like Wi-Fi and AM radio. So this is a really great place to do science. So if you want to come over here, I can actually show you a little bit about what we're doing and sort of draw some analogies to temperatures you're used to. So if we look here, this is a temperature scale going from things you deal with in your kitchen to the stuff that we can only do in these very expensive, fancy refrigerators. So if water boils at 212, and this says today's high temperature is 77. I wish it was 77. It was 34 when I got here. So we're actually closer to water freezes upstairs. But typical Chicago winter. I remember February got down to -20. That was a tough day. South Pole, where some of our colleagues go. But you need to go all the way to -495 to get to where SuperCDMS and Nexus operate. So this is very, very cold. It's not like any temperature that you've ever experienced. And the centers of these experiments are actually some of the coldest places on Earth. So you're live streaming. We're live streaming to you from one of the coldest places, definitely in Illinois, and probably on the planet. So I can actually show you the status of our experiment. So this display is what we use to control the cryogenic, the cooling aspect of our experiment. Has a little model here, and just like your fridge at home, it uses compressed gases to take a hot part and a cold part of the fridge and separate them in temperature. So outside is 300 Kelvin. We have the top of the fridge is 65 Kelvin, and it goes down in stages. So the next stage here is 3 Kelvin. It's where helium-4 liquefies. And then we have a second stage, which is around 1 Kelvin, which is where helium-3, which is a special type of helium with one fewer neutron, it liquefies at a colder temperature. And we mix those two together, and the heat of that interaction allows them to cool down the bottom here to about 14 thousandths of a degree above absolute zero. So this is a real-time readout. And we have this diagram, which
I won't go through in detail, but basically showing us how things flow and letting us open and close valves and turn off pumps and all that stuff. So we're doing all of this to cool our detectors. And what we run here are very small sensitive detectors to look for light dark matter. So I actually have, this is an exact copy of what we have in there right now. And so these are silicon chips. And so what you see is it's about a gram silicon rectangle. On the top are these superconducting sensors. And so they are the things that actually read out those very small vibrations. We sandwich that crystal between these two circuit boards. These are just normal circuit boards like you'd see in your computer. We order them from the same company. But they have wires on them that also go superconducting. So this is all electronics that are meant to work at these very cold temperatures. And we apply sort of an electric field across this thing to drift charges. And with the readout we have, we can actually see 1 electron versus 2 electrons versus 3 electrons in these detectors. And that's really what we need to see in order to search for dark matter. So this goes in the center of the experiment. And we use our very sensitive electronics to look at those very small signals. And from there, it's really about minimizing noise and understanding our environment and really making sure that our sensors perform the way we expect them to.
All right, so that's a little view into what it's like to work as an experimental dark matter physicist at Fermilab. So I'll pass it back to Dan now.
Thanks to both the younger and the present Noah. Now let's turn to Ankur to describe an experiment to look for really, really light dark matter.
Okay, cool. Good afternoon, everyone. So yeah, as Dan and Noah explained, so we are going to, I'm going to talk about very, very light dark matter, and I'm going to talk about what do we mean by wave-like nature and how we can detect it in our labs. In particular, I'm going to talk about a dark matter candidate called axion and its properties. So here, so this dark matter candidate that we are looking for, as we have heard from many talks, that we don't know the exact mass of the dark matter. So we have to scan large orders of magnitude in the mass range, all the way from thousands of mass of the protons to like very small fraction of the mass of protons. And these axions are assumed to occupy the mass range from a few micro electron volts to milli electron volts, which probably translates to a very tiny mass, like 10 raised to minus 38 to 10 raised to minus 36 grams. So it's a very tiny particle candidate, and because of its light mass, its wave-like nature is dominant, which implies that it is not localized in space, unlike heavier objects like humans. So it is basically spread throughout the space. And if these dark matter waves were crossing our lab space, it may interact very weakly with the ordinary matter, as Gordon mentioned in his talk. And the detection scheme is very similar to how we use a radio and to scan and listen to our favorite channels. The only difference is in the dark matter case, we don't know which frequency to listen to. So we have to scan a frequency by a very small amount and look for a signal, which may take years to cover 1 octave. So here I'm going to show a schematic of the actual lab experiment, where on the left you see a microwave cavity which is placed inside a magnetic field, and if the dark matter wave crosses this volume, it may interact with the magnetic field, a very weak electromagnetic interaction, and deposit a photon inside this cavity, and then we can look for a signal. So as we have also learned in all the previous talks, that for all these experiments, since we are looking for a very, very weak signal, we have to isolate the cavity from all the possible external noise sources. So we shield the cavity and we cool it to about 20 millikelvin, which is almost 100 times colder than the outer space. And Noah also showed how a dilution refrigerator looks like and how it works, which is great. So now the cavity is basically our radio, and we look for a blip in the signal as shown on the right. We can also look for a signal that is inside the cavity using these special quantum sensors, which are called qubits, to count the number of photons inside the cavity. So here is how a dilution refrigerator looks from the inside. You can see a lot of wires, and the stage that is shown here reaches about 20 millikelvin. And this is where we actually mount our detector. And in the middle, we see a microwave cavity, which is basically ready to be put inside the fridge. And on the right-hand side is a scanning electron microscope image of a qubit, which is like a classical, which is the quantum version of our classical bit, which is used in almost all our electronic devices. So with this, with all the experiments that we are doing at Fermilab and other places, we hope to answer like what is the mass or the frequency of the dark matter that we're looking for, and how does it interact. And also we need to increase the sensitivity of all our detectors so that we could listen to even weaker signals. Okay, that's it. Back to you, Dan.
Great, thanks, Ankur. So we've been describing several experiments that could possibly detect dark matter in the laboratory. I'm going to turn it over to Alex to go back out into the universe where we first saw the evidence for dark matter and tell us more about how we could find out about it there.
Thank you, Dan. So what you're seeing on your screens now is a simulation of how dark matter in the universe would cluster over cosmic time. So one thing that we do know about dark matter is that it interacts gravitationally. And since gravity is an attractive force, if you start with a relatively smooth distribution of dark matter right after the Big Bang, and you run the clock forward in time, the dark matter will attract itself and clump and cluster to form things that we call dark matter halos, which host galaxies. And so depending on the properties of the dark matter, we can actually predict what the distribution of dark matter would look like in the universe. And so if the dark matter is moving relatively slow in the universe at early times, we call this cold dark matter. So if you think back to the demonstration Dan did, when you cool down the crystals of a detector, they stop moving as fast. And this is the same idea with sort of cold dark matter. So the dark matter is cold, it's not moving very fast, and it's able to gravitationally clump into distributions that are very clumpy around our universe. If instead the dark matter was warm, had some thermal energy in the early universe, it would have a much harder time clumping. And so if we're able to, through astronomical observations, determine whether the dark matter in our universe looks more like the left-hand picture or more like the right-hand picture, we can actually learn things about the particle properties of dark matter. So Dan also mentioned that our Milky Way galaxy is sitting in this large cloud of dark matter. From our simulations, we know that this cloud is not smooth. It actually has small structures, small subclumps of dark matter sitting around our Milky Way galaxy. When we go out and look at the night sky, we actually see the stars that live in some of these clumps of dark matter. So what I'm showing here is a picture in optical light of the Large Magellanic Cloud, which is the largest satellite galaxy of our Milky Way, and actually sits in one of these smaller dark matter clumps within the larger dark matter cloud that our galaxy lives in. What we're interested in doing is trying to look for the existence of much smaller dark matter clumps. Because if these small dark matter clumps exist, we can tell that the dark matter needs to have been cold or slow moving in the early universe. So how do we find a small clump of dark matter? Well, the first thing you do is you buy a ticket to Chile. Flight prices are pretty good right now because of the pandemic. Once you get there, you drive about an hour and a half out into the foothills of the Chilean Andes. And you drive up to the top of a mountain where you have a telescope, in this case, a 4-meter telescope with a big camera on it. Because what you're looking for is a small clump of stars that's living in this small clump of dark matter. So here's what the 4-meter Blanco telescope looks like in Chile to give you a sense of scale. Inside the dome of this telescope, we have this huge digital camera. This is the dark energy camera. This was a camera that was built at Fermilab with much of the same detector technology that we actually use to make some of the detectors that you've heard Dan and Noah and Lauren talk about. So the camera is located here. It's about the size of a Volkswagen Beetle, and it's mounted something like 10 or 15 meters above a mirror, which is itself 4 meters in size. So to give you a sense of scale, this is me standing in front of the camera while it's perched atop of this large telescope. And with a camera like this, you can actually see galaxies that look like this. And this isn't the resolution of your computer monitor or Zoom dropping anything. This galaxy is actually really, really hard to see. We can actually detect it as a statistical overdensity of stars relative to the stars that we would see in the night sky. And if we go and measure the velocities of the stars in this region of the sky, we find that a large number of them are moving through space together. So this is actually a gravitationally bound cluster of stars. And in fact, this gravitationally bound cluster of stars is moving internally much faster than we would predict if it was only normal matter there. In fact, there's hundreds of times more dark matter in this picture than there is matter in stars. And so we started off looking for galaxies like this. We've been able to search for galaxies that look like this and live in these small dark matter halos. And that allows us to go back to this picture here and say that, in fact, this is not the situation with dark matter. Dark matter cannot be warm in the early universe. It doesn't tell us for sure that dark matter is as clumpy as the picture over here, because there are even smaller clumps of dark matter predicted where we haven't been able to find galaxies yet. But with our larger and larger telescopes and more sensitive cameras, we're actively looking for the stars that would live in these clumps of dark matter. So I'm gonna hand it over to Nhan.
All right, so I hope you can see the slides here. Sorry, so I'm gonna talk a little bit about, you've heard, I guess, about how people are looking for dark matter, both by observing what's going on in our universe and experiments for detecting the dark matter that's around us. So I just want to walk through a couple of examples here. And what I want to get to is another way of sort of searching for dark matter, which is dark matter at accelerators. Okay, so so what you've heard described thus far in terms of understanding sort of what dark matter is at the particle level is that you have some dark matter particle around us. It interacts with our detector, which I call here as a normal particle. And then, okay, that dark matter particle goes on its way, and then you see some effect of this interaction through, for example, in Dan's example, this vibrating crystal. One thing that we haven't talked about, another way that people look for dark matter is by actually looking out into, let's say, for example, our galaxy, and looking for maybe signatures of when two dark matter particles interact, and then they make a special signature, which we see, which are the normal particles that interact with our detectors. Let's say in here, and I have an example of electrons, protons, neutrons, and so on. What I want to talk about is another way in which we can look for dark matter, which is through producing them at accelerators. So we actually can take a a beam of normal particles, and we can smash them into other normal particles, and hopefully, in a very rare case, make dark matter. So I'm going to be talking about the case when you take a normal particle and you smash it into something, which is called fixed target. And Matteo, who's coming next, is going to talk about when we take two particles and we collide them together. And so what are the nice advantages of this particular approach? Well, one, it's a way to make dark matter in the laboratory, and you have some more control over the process in some sense. And then the other part is that when we make these beams of particles, they're actually very high energy, which we call relativistic beams, and this in some will help recreate early universe conditions. All right. So before getting a little bit deeper into this, I wanted to talk about the motivation, or one of at least my personal motivations for looking at dark matter this way. And so there's one assumption that I want to make here, and that's that dark matter is in thermal equilibrium in the early universe, and I'll talk about that, what that means here in a second. But that helps us narrow down the mass range where we could be looking for dark matter to sort of this range which is MeV to TeV, and if you don't know what those mean, I just put some sort of guides here, which is electron mass to proton mass. And so I'll focus on the lower part of this spectrum from electron mass to proton mass, and Matteo will talk about just above the proton mass and in this scale. Another way that sometimes I like to describe this is that normal matter lives here, and so why might dark matter also not live in this same area? So just getting back to this one assumption here that dark matter is in thermal equilibrium. So what this means is that you make the assumption that at some time in the early universe, dark matter and the standard model, or normal particles, were in thermal contact, or so in a hot soup where let's say the conversion from dark matter to the standard matter particles and vice versa are at the same rate. So this is the assumption that you make, and then you start looking in this smaller mass range or more narrow mass range. So how do we do this? So first we need an accelerator, and so this is a picture of the Fermilab accelerator complex here. This is stretched out over many miles of accelerator beam line to get the particles up to those relativistic energy scales, and then you need a detector. And so here's a case of a fixed target experiment. Actually, this is two kind of in one, but you hit a target and then you look for signatures of dark matter, either by inferring that dark matter exists by the absence of energy, or actually by seeing it in a downstream detector. So you make a dark matter particle here, you might not see anything in this detector, or you might see something in this detector. So those are the two main elements. So what makes this so technically challenging? So this is an example. This is that same setup here where you have the particles coming in, it hits this target, and then you need to try and infer its existence to the lack of momentum. So first, as you've heard many times now, our standard model, or normal particles, they only interact very weakly with the dark matter. So you need a lot of our standard model particles. For this particular experiment, you need a lot of these beam particles. And so to get a lot of them at the right rate to be sensitive to dark matter, we need to have 37 million particles per second coming in. So this is now you need a detector that's able to read out its signals very, very quickly. You need cutting edge detectors. We're basically just firing a lot of particles onto these detectors. And so they have to be they have to be able to withstand the amount of radiation that they're getting. And then what the actual signature we're looking for is you have a beam coming in, then it loses some of its momentum, and the rest of it is leaving as dark matter. And so in this case, to see our dark matter and to infer the existence of dark matter, you really have to understand everything else that is happening in one of these detectors. And so this is very, again, you heard a lot about very sensitive detectors, and that's very, very important in this accelerator case as well. I just wanted to close up by just showing a schematic of a detector that we're developing. So this is the sort of technical drawing of the experiment, or the cartoon I just showed in the previous slide. And just to give you a sense of scale, this is sort of at the meter size here. And this is sort of a fancier drawing of that detector. All right, so that's it for me. And then I think Matteo is going to follow up with a similar type of experiment, but at higher energies.
I'm gonna share my slides, and I'll try to pick it up from where Nhan left off. So Nhan described very nicely the different pieces, the different ingredients that we need in order to produce dark matters at laboratories. And the first very important ingredient is having a particle accelerator available. Nhan described the particle accelerator that is needed for what it's called fixed target dark matter searches. I will describe a little bit what we can do if you have available a very, very, very large particle accelerator like the Large Hadron Collider at CERN in Geneva. In this picture, you can see an aerial visual of the accelerator. You can have a sense of the scale quite easily here. So the diameter, well, the circumference of this particle accelerator is 27 kilometers. It means that, yes, it's nominal in Geneva. Geneva is on the bottom left of this picture, but it goes far beyond the boundaries between Switzerland and France. And you can see in this picture, not only the scale, but you can see several different names mentioned all around this circumference. And these are the different experiments that are taking data collected by what's delivered by this particle accelerator. So what's delivered by this particle accelerator are collisions between two normal particles, two beams of normal particles, and more specifically two beams of protons. So you have protons coming from the left, protons coming from the right. They collide inside what is called the collider experiment. And in this case, I picked the name of the experiment we at Fermilab are contributing to, that is called CMS. The CMS experiment uses a CMS detector, and you can see a schematic vision of this detector in this slide. I picked this picture on purpose because it's very chaotic, and this chaos gives you an idea of the complication of the detector that we're using. Not only the complication, but you can see on the bottom right of this picture how it scales with respect to the size of a human being. That appears to be very, very little with respect to this very, very big particle detector and this very, very complicated particle detector. I will go into a little more details on why we need such complication in the detector in order to do the physics we do, and how it matters when we use this device in order to search for dark matter. And this is a very nice picture that tells you what happens inside the detector. So this is a sort of a three-dimensional view of the detector that we've seen in the previous slide. And that gives you an idea what happens when the two protons beams collide inside the detector. You may know the very famous equation from Einstein that mass and energy are pretty much the same thing. So if you are colliding two proton beams at very, very high energy, in this case 14 tera electron volts, that means a lot of energy, that energy can be converted in mass. That means a lot of particles are created. You can have a sense on how many particles are created by looking at this picture, and all these different mass, these different colors are the energy that is deposited by each and single particle that is created in a collision. So a lot of particles are created. These particles go everywhere in the detector. They leave an energy that is captured and analyzed by physicists that work with this device. On this slide this is a two-dimensional view of the detector. So on the bottom left of this slide, you see there is actually a transverse slice of our CMS detector. And here you can see that all the different colors that I showed in the previous slide are actually together in order to understand which kind of particles has been produced in the collision. Again, protons collide, they generate particles. These particles leave energy. These energies are left in the different subcomponent of the detectors. And here come into place the complication that I mentioned before. The detector has to be complicated because we need to understand where the energy deposit happened and put together all these different energy deposits to say, okay, a muon has been produced in this collision, an electron has been produced in this collision, and all these different particles leave different signals in different places of the detector. So this is what happens pretty much when you generate normal particles, known particles. This is what happens in the detector when possibly a dark matter particle is generated. Nothing. And that's due to the fact that, as mentioned before, these dark matter particles are supposed to interact very weakly with common matter, and the detector is made of common matter. Therefore, we are not expecting dark matter to leave any energy deposit inside the detector. So this makes detecting dark matter particles at collider experiments very, very challenging. But there is a technique that we can use in order to do that. And so on this slide, you can see a three-dimensional and a two-dimensional view of the detector again, that gives you an idea on which strategy is applied in order to detect these particles. So another important rule in physics is the energy is conserved. It means that if we see a production of a visible particle, like here in the three-dimensional view, or like here in the two-dimensional view of our detector, and we see nothing else, we can infer the presence of something that is invisible to our detector by simply imposing the energy conservation. So it cannot happen that just this particle is produced. Something else should recoil against this particle in order to preserve conservation of energy. So this red arrow that is here is actually not visible, is indicating the absence of something, and the absence of something is the quantity, the evidence that we have of something invisible being produced, like for example, a dark matter particle. So that gives you a sort of an idea on which is the strategy to search for dark matter at collider experiments, and gives you an idea of the challenge that brings. With that, I will give this back to them.
Okay, thanks very much, Matteo. So we've finished talking. We'd like to answer any questions that you might have. We've been trying to answer some of them as we've gone along, but let's see if there's more. Becky, do you have some more questions?
Yes, I do. So we have a few more questions for people, and I think a number of the questions that have been answered, I might also just ask them again, to give everybody a chance to weigh in. So one question that someone had is dark matter a distorted galaxy?
Maybe I'm the galaxy expert in the audience. So we believe that that all galaxies actually live in clouds of dark matter, and so while that dark matter imposes a gravitational influence on the galaxy, it is of itself not a distorted galaxy. The gravity from dark matter in galaxies can bend the light from galaxies that are actually behind a galaxy of interest and act like a lens, and a slightly out of focus lens. And so in that case, you are distorting the image of a background galaxy, but that's actually a bending of the light and not so much a distortion of the galaxy itself.
So we also have someone asking, what as an undergrad in physics should I focus on to learn more about dark matter?
So I can feel that one. As we've seen so far, there's a broad range of possibilities for what dark matter is, and a broad range of strategies for trying to discover it. And so just about any course that you take will have some sort of connection to the topics that we've discussed here. So anything related to astrophysics or to cosmology. If you have a general relativity course, that would be a very good place to make contact with it, or perhaps an introduction to elementary particles to see how that might fit into the bigger picture of what we know about forces and how subatomic stuff interacts with other things.
Great. We had another question that I think has been answered in the question section, but I want to open it up. What is the link between black holes and dark matter?
I think the honest answer is we don't know whether there is a link between black holes and dark matter. Gordon touched on the possibility that primordial black holes could be part of the dark matter. That's a testable hypothesis, but right now we can't say whether there's a link or not.
I just wanted to add one little fun fact about black holes, that so it might not be true that black holes and dark matter are the same thing, that dark matter could be any number of things, including black holes, but that's not required. However, black holes are believed to evaporate. That if you have a black hole, it doesn't live forever. So over time, it sheds its mass and radiates particles. And it can also produce dark matter as part of that radiation. So that's just an interesting side fact.
Awesome. So another question, what motivates all of you in searching for more about dark matter? Is it knowledge for knowledge's sake, or is there something more?
We need multiple opinions on this. I'm the oldest, so I'll tackle that first. I've been working in this for quite a while. I find it really compelling that we can do experiments here on Earth that could detect particles that have only been detected by their gravitational influence on things that we can see in telescopes. And, as a side effect, we get to make really cool detectors that are very sensitive, that, they're fun to build and fun to operate. So it's a pleasure on both sides.
So how do we, another question, how do we come up with potential candidates for dark matter?
So that's a good question. As we've seen, there's a really broad range of possibilities for what dark matter can be. The most agnostic way that you could do it is you just take the evidence at face value, the list of observations from Dan's talk at the very beginning, and those don't really narrow it down too much, that you could almost throw a dart on a board of possibilities, and any one of those could give you a sensible dark matter candidate as long as it satisfies those requirements. But usually what motivates some people who think about the theoretical side is that there are other unsolved problems in physics. Like, for example, why is there more matter than antimatter in the universe? Or why is gravity so much weaker than the other forces that we've discovered in nature? And so sometimes people will propose larger theoretical frameworks to address some of those problems. And as a bonus, they might have something to say about dark matter as well. And so many of the strategies that you've heard about today are aimed at detecting dark matter that comes from other theoretical explorations along these lines.
So I think building on that a little bit, what might be an experimental strategy for detecting the influence or existence of an as yet unknown fifth force of nature?
Well, I think if we actually do detect dark matter interacting with normal matter, it's very likely a fifth force. It could be the weak interaction, as Gordon said, but we've almost covered that territory. And so, it's more likely that it's a very, very weak force that we haven't seen in normal matter yet. And there's possibilities that the dark matter is made up of multiple particles that interact with themselves with their own forces, and there's possibly some very weak connection between the dark sector and our normal matter sector.
And there's a great question talking a little bit about that. Would all of dark matter be a particular type of particle or a whole class of many different particles that can interact with each other and form different types of dark structures, i.e. dark molecules?
Yeah, so that's actually a possibility. There are some theoretical papers on what that would mean. It's probably a little naive for us to think that dark matter is just one particle. I mean, we look at what we're made out of, and it's tons and tons of stuff. And that forms all kinds of structures. The only thing that we have to make sure of when it comes to dark matter is that by postulating the existence of things like structures, you don't somehow prevent dark matter from being able to do the things that we've already discovered by studying galaxies and the large scale structure of the universe. So as long as the structures that it forms still enable it to be stable over time and to help galaxies form and influence the rotation of galaxies, then that's still a perfectly good possibility.
Could dark matter be a stellar object composed of large quantities of neutrinos?
I can take that one. So if you're talking about the neutrinos that we know about, then those neutrinos are indeed produced in the early universe, but they are such low mass that they're moving at a speed that is close to relativistic. And so in the early universe, they would behave as something that we would call hot dark matter. And that hot dark matter is inconsistent with the observations that we have of the formation of structure and galaxies and dark matter, the dark matter web. And so we are pretty confident that the neutrinos that we are familiar with are not making up the dark matter. That said, there is a possibility that there are additional heavy neutrinos that we have not seen evidence for yet that could be making up the dark matter.
Awesome. Could there be a dark universe out there?
I mean, the question gets back to the question of whether there can be multiple constituents to what we would call like a dark matter sector. And that is still very much a possibility. And you could even say that our universe is actually the dark universe, because if you take into account dark matter and dark energy, 95% of our universe is indeed dark.
How could, this is also a little more sci-fi, how could dark matter possibly help or hurt space travel? Or have no effect? That is also an option.
As far as we know, it wouldn't have any effect. I mean, we started out talking about the fact that dark matter and normal matter don't interact much. So if your spaceship is built out of normal matter, it should just zip through dark matter pretty quickly. It's not like Star Trek where you run into dark matter nebulas or anything like that.
So I have a question for you. How will you be sure that what you have found is actually dark matter?
Maybe I'll take this one since I haven't spoken yet. I think that's why you heard about so many different and diverse ways of looking for dark matter. If we think we see a signal in one experiment, we'll most certainly want to try and confirm and understand what it would look like in a different experiment.
Awesome. Well, thank you guys so much. We've recorded this and we will post it shortly and make sure that everybody gets the URL to where it's posted. And please, 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 for more about dark matter, follow us at Fermilab on Twitter and Facebook and the Fermilab fnal.gov site. We've got a lot of great experiments and we'd love to tell you more about them as we move forward. And happy Halloween. If anyone is looking for a Halloween costume, dress as a neutrino, you don't even have to talk to anybody. So have a great afternoon and thank you so much for joining us.